Okay, and so I'm going to start talking about Newton's third law. And the definition of Newton's third law, or what it is basically just every action has an equal and opposite reaction. And when they say action and reaction, what they're really talking about is force. So, so every force has an equal and opposite force. And the other thing is that forces come in pairs. There's no force in the universe that is by itself. So I'll explain this in a little bit more detail in a moment. But every action has an equal and opposite reaction. You've probably heard that before. So here's just a general example, an easy example. Let's say I have a block. We'll call these blocks just block A, and I push on the block with my frumpy, weird hand. Um, this block is going to feel an applied force from my hand to the right, and my hand feels an applied force from the block to the left. And these forces are equal and opposite. So this is what's called an action reaction pair. Cool. That should be, I think so far, if I'm assuming right, you guys are probably still good. Like, this is all making sense so far. But there's a couple misconceptions that my students have. Um, so, for example, let's say that I take that block, same block A, and instead of looking at the push on it, let's just look at the force of gravity on it. Um, let's and feel free. We'll see how it goes. Can anyone tell me what the reaction force to that would be? Just in the chat, or you can, if you want to be recorded, you can unmute yourself. Sean is saying normal, normal from Fiona. Any others? Normal, normal, normal. Right? Yeah, that's what I was expecting you guys to say, and you fell perfectly into my trap. Normal and gravity are equal in this scenario. Not all scenarios, but in this scenario they are. And they are opposite in this scenario as well. Again, not in all scenarios, but in this one they are. But they are not action reaction pairs. These are not pairs. They just happen to be equal and opposite, but they're not an action reaction pair. And here's how I'd like you to understand that. Let's use a different notation for, I know, thank you, Marissa, yeah, gasp. Let's use a different notation for this. Fg, that's a force of gravity from the Earth on, we'll call this block A, Earth on A. And the normal force is the force from the table on A. In order to figure out what the reaction forces to those things are, this is all you have to do. It's very easy. Switch the objects. So the reaction force to this would be the normal force of A on the table. And the reaction force to this would be the force of gravity of A on the Earth. So it's a very simple mechanic. All you do is, if you write out what the object is that's exerting the force and what it's exerting it on, and you just flip those, that will tell you what the reaction force is. But here's the thing. We kind of like, and by we I mean me, I kind of just glossed over this idea, but let's just think about this for a second. If, let's say, who do I want to pick on? I pick on a lot of you guys all the time. Let's say Fiona. I never pick on, actually, that's not true. Yeah, Fiona. Sorry. Fiona's falling from the sky. And she's falling and accelerating because there's a force of gravity on her. The reaction force from the force of gravity of Earth on Fiona is the force of gravity of Fiona on the Earth, which means that Fiona is pulling up on the Earth with just as much force as the Earth is pulling down on Fiona. And that is absolutely true. There's no like trick there. That is the truth. She is pulling on the Earth as much as the Earth is pulling on her. The difference, though, the reason why we see an acceleration of 9.8 for Fiona, and we see an acceleration of 0 for the Earth, is because of the difference in mass, right? If you look at Newton's second law, acceleration is equal to the net force over the mass. Well, if the net force is the same each time, so I'll start with the net force on Fiona. We'll call it Fiona like that. Then it's the mass of Fiona, which is little baby mass compared to the Earth. And so that means we're going to have a big acceleration for Fiona. Whereas if we have the Earth with the same size force on it, right? So these are all the same size, Earth force on the Earth, and divided by the mass of the Earth, which looks something like this. Give me 1 second to have some room here. Which looks more like this, right? Mass of the Earth compared to Fiona. And that's going to give us a little baby acceleration. And that acceleration is going to amount to like 0.000000001, which means that the Earth is not going to accelerate really at all. But Fiona is going to accelerate at 9.8 because she's in free fall. So that's just one misconception that my students have, that normal is always opposite to gravity, so that makes it an action-reaction pair. That's false. And also they're like, well, wait a second, you can't have a force of the Fiona on the Earth. But yeah, we can. They are an action-reaction pair, and they're equal and opposite. The last thing I'll say is this. There's a lot of questions on the AP exam, and by a lot, I mean a couple. There's a couple questions on the AP exam that really try to trick you, and they try to feed into that misconception. They want you to think that something has to pull on something else harder. Like here's an example that we use all the time. It's called the horse and the chariot example. It's a very famous physics example. So here's my chariot cart, and it's being pulled by a horse. Please forgive my drawing. I'm not an artiste, but you guys can just imagine this is a horse, right? Mane, I think, and like an ear. Horses have ears, I think, and a snout. Is that what they're called? I don't even know. Just a ripped horse. Just a big chunk of a horse. No nostrils, eyeballs, brows, mouth. Happy. Anyway, I always do this. I always draw the wheel like way too high up. It's got to be touching the ground there. Anyway, here is, who am I putting in there? Somebody that hasn't even talked. Audrey. This is Audrey. Okay. There she is in the chariot, very happy. So here's the question. If Newton's third law is true, which I'm telling you it always is, if it's true, how, no, the question is, how do they ever get started to move, right? Because if the horse moves to the right, I'm just going to erase this real quick. If the horse moves to the right and pulls on the chariot, doesn't the chariot pull back on the horse? And won't they just cancel out? So if Newton's third law is true, how can the horse move forward and pull the chariot, and the chariot pulls back with an equal and opposite force? How do they ever get to move if they're at rest to start with? So that's kind of the trick here. Sorry, let me just read a question. Doesn't that mean that in free fall, gravity makes the object have a slower acceleration if it has a larger mass? Does that question even make sense? That question does make sense. I'm going to answer that in a moment. Let's just stay on the horse and chariot for a second, and I'll answer that question, Nanda. So here's the thing. I'm just going to answer this for you because we don't have lots of time. The thing is that, yes, the forces are equal and opposite, but those forces are happening on different objects, and each object has its own force diagram, so they can still accelerate. So for example, this would be the force diagram for the horse. Of course, you have gravity, you have normal, and the horse is, actually, let's start with the chariot. That one's a little easier. So we have gravity, we have normal, Sorry, that's supposed to go straight up. And then we're being pulled to the right. We'll call it an applied force from the horse. And maybe there's like a little bit of friction, but not enough to be bigger than the applied force. So we're still accelerating to the right. So we're good with that, right? Then, and these are equal to each other. Then for the horse, we have normal and gravity for the horse. And then the horse is being pulled back with an applied force. And these two forces are action-reaction pairs. They're on different force diagrams, but they're equal to each other. And that's nice. But the horse is being pushed forward because of the ground, right? The horse's feet are pushing backwards, pushing the ground backwards, and the ground is pushing it forwards. Just like when you put your canoe or your oar in the water, you push the water backwards and the water pushes you forwards, right? That's an action-reaction pair right there, right? So the ground is pushing the horse forwards, and that force is just happens to be bigger than the applied force from the chariot pulling backwards. All right, so that's how we get around that, and so the main point here is that action-reaction pairs happen on separate free body diagrams, which means they can never cancel. All right, so that's kind of just me addressing all the misconceptions with Newton's third law. The last thing I'll say before I answer Nanda's question is Newton's third law is always true. So if somebody's like, oh, I'm pushing a car up a ramp and we're accelerating up the ramp, right? And you're like, oh, definitely the person is applying a bigger force on the car than then the car is pushing back on him, right? Because they have to be accelerating, right? So the person's pushing with a force like this, and the car might be pushing like that, but it's not big enough. No, that's not true. The car pushes back with an equal force than the person pushes on the car. It's always true, no matter what. All right, so let me answer Nanda's question real quick. I think I know what Ananda's asking, but this is good to bring up anyway. He says, doesn't that mean that in free fall, gravity makes the object have slower acceleration if it has a larger mass? So acceleration is equal to this. This is Newton's second law, right? And so if you have a certain mass, the bigger the force on it, the bigger the acceleration, right? Well, if the object has a bigger mass, if this goes up, then this is going to go down, right? So I think Nanda's saying if the mass is bigger, then the acceleration is going to get smaller, and that is true. But the problem is that when you increase the mass, the net force on it also increases, and this stays the same at a constant 9.8, because the net force on an object in free fall is the force of gravity, and the force of gravity is mass times g. So if you increase the mass, then the force of gravity increases. If that increases, then the net force increases. And if the net force increases and the mass increase proportionally, then this just stays the same. Does that answer your question, Nanda? That's how all things accelerate at 9.8, because even though they're more massive, the Earth is pulling on them with a bigger force. So like a picture would be like, here's a little ball and here's a big ball, right? This has a big mass and this has a little mass. And so this one has a little force of gravity, but this one has a big force of gravity. And so the acceleration here would be A is equal to big F, because this is Fg, and then big mass, so you get A. And then this one is going to be regular A, and you get little force over little mass. So the proportions are still the same. Okay. I'm glad that helps you understand. All right, so I'm going to stop recording here for Newton's third law, and thank you for joining my TED Talk.